Okay, welcome back everyone. In this video, we're going to be looking at what happens when a force is varying, either with time or with distance, and we're going to look and see how we can calculate work. Okay? We're going to focus on a force which is changing as a function of position. And later on in the unit on momentum, we'll look at what happens when the force is changing as a function of time. So the concept will be the same or very similar, and the math will be very similar as well. Okay, so we already know that when a force is constant, work is equal to F times R. But if a force is variable, you can't move very far until the force is different or has changed. The force is only constant over an infinitesimal displacement, which we call dr. Okay, so this is a very small amount of displacement. And likewise, dw is a very small amount of work. It's not The Sister from Arthur, if any of you know that show. But what we have to do is, if we want to calculate work for a larger displacement, we need to add up all of these dw's. And so the concept is that work is the integral of dw, which is the integral of f dot dr. Now this kind of thing over here, work is the integral of dw, this is kind of the basic idea for all of integrals. And we're going to be coming back to this again and again. We'll be doing this to calculate the amount of charge, to do electric field, to do voltage. So this kind of calculation where we split something up into a small piece and then integrate, well, this is really very important to the course overall. So it's something that you want to practice. So what does it look like if you have a variable force? Well, here's f of x, which can change, and we're going to go from x equals xa to x equals xb. And the area under this curve of force versus displacement is going to give us the work. Okay? So one way to think about this is that we can calculate a dw by taking f of x times dx. In other words, we're going to split this into lots of tiny, tiny little rectangles. Okay, now for the purpose of this rectangle, if it's really small, the height of it is the value of the function at that point, f of x. The width of it is going to be dx. So that means that the area is the height times the width, f of x dx. And then if we take the integral of this, then what we're doing is we're adding up all of these rectangles. Okay, now there's fancy math rules, the trapezoid rule, the left side, the right side, all these Riemann sums. We're not going to worry about that. We're just going to calculate the work as the definite integral from xa to xb of f of x dx. So let's see an example where we don't really have to integrate, and then we'll look at one where we do. Okay, so we want to find the work done by this force as the particle moves from x equals 2 to x equals 8 meters. So we kind of mark this off here and mark this off here, and we know that what we need to do is find area. Okay, so maybe I'll just do this, and now I just have 3 areas to find. 2 triangles and a trapezoid. Okay, so this guy here will be 1/2 times base 1, which is 20, plus base 2, which is 30, times the height, which is 2. Okay, so that's going to be 50 times 2 over 2, or just 50 joules. This guy right here, this triangle, is going to be 1/2 times the base times the height. And so that's going to be 15 joules. And notice that I have newtons and meters, so I know that my units will be joules. And this guy here is going to be 1/2 times the base, and the base is going to be 8 minus 5, or 3, and the height is going to be actually negative 20. So yes, negative work can occur, and in this case we have negative 30 joules of work. So the total work is the sum of these, 50 plus 15 minus 30, or in other words, let's see, I think I can do math. Is that 35? Yeah, that's 35 joules. Okay, so now what do you do if you have a changing force? So f of x is 4x minus x squared, and that's in newtons. We want to find the work as the particle moves from x equals 0 to x equals 2. And I just want to remind you that if you have a function ax to the n, that the integral of this function is ax to the n plus 1 over n plus 1. Okay, and that would be with respect to dx. We would do plus a constant, but when we have limits on this, then we would evaluate it. Okay, so the guiding principle here is that work is going to be the integral of dw. Okay, and so work is going to be the integral. And just to try to understand how to do these limits a little bit better, let's say this is from x equals 1 to x equals 2. So we put in 1 and 2, and we put in f of x dx. Now, what does this function actually look like? Well, it starts at 0 and it goes up and comes down. So if this is f of x, and this is dx, or x rather, we're trying to find this area. Okay? So the work is going to be the integral from x equals 1 to x equals 2 of 4x minus x squared dx. And this is going to turn into, well, this is x to the 1. It will increase to x to the 2, and then 4 divided by 2 is 2. And then this will turn into x to the 3 and be divided by 3, evaluated from 1 to 2. Now, one thing that people sort of have a hard time with when they're first learning integrals is what happens to this dx when you integrate? Well, remember the concept is that dx is part of the area of this tiny chunk. So when we add up all the areas, the dx is just gone. Okay? So we're going to go ahead and evaluate this. Okay? So first we're going to have 2 times 2 squared, which is 4, minus 1/3 times 2 to the cube, 2 cubed, which is 8. And then we're going to evaluate this when x is 1, so it'll be 2 minus 1/3. Okay? And so we're going to have basically 8 minus 8/3 minus, and that's going to be 5/3. Is that right? 2 is 6/3, okay? So 8 is actually 24/3, so that's 16/3 minus 5/3. So the total work that's done is 11/3 joules, or something like 3.7 joules if I'm doing my conversions correctly, my fractions, okay? So that's kind of how you set these up. Let's do another example. Let's find the work done by a spring as it's stretched from its equilibrium position. Now, in our unit on forces, we learned that the equation for the spring force is equal to kx. Now, there's a negative sign in there that indicates that it's a restoring force, but we'll just take the magnitude from now, okay? And we want to find the work from x equals 0 to x equals a. Okay, so a is right here. Okay, well, we can't just say kx times a because the force is changing. It starts at 0 and then it goes up to a maximum of ka. Well, we can't say that it's equal to ka squared either because we have a triangle. So we have to integrate, okay? Oops. So the work is going to be equal to the integral from 0 to a of kx dx. And kx is just going to turn into 1/2 kx squared, evaluated from 0 to a, so that's 1/2 k a squared. Okay, so that's the work done by a spring, and that actually happens to be the energy stored in a spring as well. So remember that for next time. Okay, now finally, how much work does an applied force do when it stretches a nonlinear spring where the force varies in this fashion? Okay, well again, work is the integral of f dx, and we're going to go from 0 to 0.2 in meters. So we want the integral from 0 to 0.2 of 300x minus 25x squared. We're going to leave all the units out because we know it's going to end up in joules. And so this is going to be 150x squared minus 25 thirds x cubed, evaluated from 0 to 0.2. And when we do the math for that, that's going to give us about 5.93 joules. Okay, so the evaluating is not really all that tricky. It's just learning to take the force and integrate it in order to calculate work. Okay, so next time we're going to look at how work ties into energy by introducing the work-energy theorem.